In the vast expanse of space, where billions of stars dance across the cosmic stage, there exists a fundamental rule that has governed our universe since the beginning of time. This rule tells us that nothing, absolutely nothing, can travel faster than light. For over a century, scientists have accepted this as the ultimate speed limit of reality itself. Light races through the vacuum of space at an incredible 299,792,458 meters per second. This number has become sacred in physics, a constant that shapes everything we know about space, time, and existence. But what if this sacred limit is not as absolute as we believe? What if, hidden in the depths of quantum mechanics or lurking in the shadows of cosmic phenomena, there are ways to bypass this cosmic speed limit? What if we are already witnessing faster than light phenomena all around us, but we simply do not recognize them for what they are? Tonight, we embark on a journey through the mysteries of the universe, exploring the tantalizing possibility that the speed of light might not be the final word after all. We will venture into realms where space and time bend to our will, where particles dance instantaneously across vast distances, and where the very fabric of reality might be more flexible than we ever imagined. Consider this for a moment. Every night when you look up at the stars, you are seeing ancient light that has traveled for years, decades, or even centuries to reach your eyes. The light from our nearest star neighbor, Proxima Centauri, takes over 4 years to reach Earth. The light from distant galaxies has been traveling for billions of years. This cosmic delay has always reminded us of our place in the universe, isolated by the vast distances and bound by the speed of light. But what if there were shortcuts through space itself? What if the universe contains hidden pathways that could allow us to step from one side of the galaxy to another in the blink of an eye? What if the particles that make up your very being are already connected to particles on the other side of the universe in ways that transcend our understanding of space and time? These are not just the dreams of science fiction writers. These are serious questions being explored by the brightest minds in physics today. From the exotic mathematics of warp drives to the strange behavior of quantum particles, from the theoretical existence of wormholes to the mysterious properties of dark matter, science is uncovering phenomena that challenge our most basic assumptions about the nature of reality. The story we are about to explore together is one of human curiosity pushing against the boundaries of the possible. It is a story of scientists who dare to ask whether the laws of physics as we understand them are complete, or whether they are simply the first chapter in a much larger book of cosmic knowledge. As we drift through this exploration together, allow your mind to wander through the possibilities. Let yourself imagine a universe where the speed of light is not a prison that confines us to our small corner of space, but merely the first rung on a ladder that leads to unimaginable discoveries. Tonight, we question everything we thought we knew about the ultimate speed limit of the universe. To understand why the speed of light holds such power over our universe, we must first appreciate just how extraordinary this speed truly is. Light travels at 299,792,458 meters per second through the vacuum of space. To put this in perspective, light could circle our entire planet Earth 7.5 times in just 1 second. In the time it takes you to blink your eyes, light has already traveled thousands of kilometers through space. This incredible speed was not always known to humanity. For centuries, people believed that light traveled instantly from one place to another. Ancient philosophers debated whether vision worked by light entering the eye or by the eye sending out invisible rays to perceive objects. They had no concept that light itself was traveling at any measurable speed at all. It was not until 1676 that a Danish astronomer named Ole Rømer made the first measurement of light speed by observing the moons of Jupiter. He noticed that the timing of these moons seemed to change depending on Earth's position in its orbit around the Sun. When Earth was farther from Jupiter, the eclipses of Jupiter's moons appeared to happen later than predicted. When Earth was closer to Jupiter, the eclipses happened earlier than expected. Rømer realized that this was because light from Jupiter's moons took longer to reach Earth when our planet was farther away. This was a revolutionary discovery. Rømer had proven that light did not travel instantaneously, but had a finite speed. His measurements were not perfectly accurate by modern standards, but they were remarkably close. He estimated that light traveled at about 214 million meters per second, which was quite impressive for the 17th century. Over the following centuries, scientists refined their measurements of light speed using increasingly sophisticated methods. In 1849, French physicist Hippolyte Fizeau used a rotating toothed wheel to measure light speed. He sent light through the gaps between teeth in a rapidly spinning wheel, across a distance of several kilometers, and back through the same wheel. By adjusting the speed of the wheel's rotation, he could control whether the returning light would pass through a gap or be blocked by a tooth. This allowed him to calculate light's speed with remarkable precision. Later, Albert Michelson improved upon these methods using rotating mirrors instead of toothed wheels. He bounced light off mirrors that were spinning at precisely controlled speeds, measuring the tiny shifts in the light's path caused by the mirror's rotation during the light's journey. Michelson's experiments were so precise that he won the Nobel Prize in Physics for his work. His measurements of light speed were accurate to within a few meters per second of the value we accept today. By the late 1800s, scientists had determined that light speed was remarkably constant, always traveling at the same rate through empty space, regardless of the motion of its source or observer. This constancy became one of the most puzzling discoveries in all of physics. Common sense tells us that speeds should add together. If you throw a ball forward while riding in a moving car, the ball's speed relative to the ground is the speed of the car plus the speed of your throw. But light behaves differently. Whether light comes from a stationary source or from a source moving at tremendous speed, it always travels at exactly the same rate when measured by any observer. This strange behavior of light troubled physicists for decades. How could something maintain the same speed, regardless of the motion of its source? The answer would revolutionize our understanding of space and time itself. It would show us that the universe is far stranger and more wonderful than anyone had ever imagined. The breakthrough came from understanding that light is not just any ordinary phenomenon. Light is electromagnetic radiation, a ripple in the electromagnetic field that permeates all of space. This field exists everywhere in the universe, filling every cubic centimeter of empty space with invisible energy. Disturbances in this field propagate at a specific speed determined by the fundamental properties of empty space itself. The speed of light is not arbitrary. It is woven into the very fabric of reality. When we look deeper into the mathematics of electromagnetism, we find that the speed of light emerges naturally from two fundamental constants of nature. These constants describe how electric and magnetic fields behave in empty space. The first constant determines how strongly electric charges attract and repel each other. The second constant determines how strongly magnetic fields interact with electric currents. When you combine these two numbers in a specific mathematical way, out pops the speed of light. This revelation showed scientists that light speed is not just a measurement, but a fundamental property of the universe itself. The discovery that light is electromagnetic radiation also explained many other mysteries. It explained why light can travel through the vacuum of space even though there is no medium to carry it. Unlike sound waves, which need air or some other substance to travel through, light creates its own disturbance in the electromagnetic field. It also explained why light exhibits both wave-like and particle-like properties, a duality that had puzzled scientists for generations. But why should this speed be a limit? Why can nothing travel faster than light? The answer lies in understanding what would happen if something could exceed this cosmic speed limit. As objects approach the speed of light, strange things begin to happen to them. Their mass appears to increase, making them harder and harder to accelerate. Time itself begins to slow down for the object relative to outside observers. Space contracts in the direction of motion. These effects become more and more extreme as an object gets closer to the speed of light. To actually reach the speed of light, an object with mass would need infinite energy. This is nature's way of enforcing the speed limit. The universe itself conspires to prevent anything with mass from reaching or exceeding the speed of light. Imagine trying to accelerate a spacecraft to ever higher speeds. At first, the energy required increases gradually. But as the spacecraft approaches half the speed of light, the energy requirements begin to grow dramatically. At 90% of light speed, the energy needed is more than twice what it was at rest. At 99% of light speed, the energy requirement is 7 times greater. At 99.9% of light speed, it becomes 22 times greater. This pattern continues without end. The closer you get to the speed of light, the more energy you need to go just a little bit faster. To reach exactly the speed of light would require infinite energy, which is impossible to obtain. This mathematical impossibility becomes a physical barrier that protects the speed of light as the ultimate speed limit. For particles without mass, like photons of light itself, the situation is different. These massless particles must always travel at exactly the speed of light. They cannot go faster or slower. They cannot be at rest. From the moment they are created until the moment they are absorbed, they race through space at this constant, universal speed. In a very real sense, photons are pure speed, existing only in motion. This speed limit has profound implications for our place in the universe. It means that the stars we see in the night sky are not showing us the universe as it is now, but as it was when the light left those distant suns. We are looking into the past with every glance at the heavens. The light from our sun takes about 8 minutes to reach Earth, so we see the sun as it was 8 minutes ago. The light from the nearest star, Proxima Centauri, takes over 4 years to reach us. We see it as it was 4 years in the past. For more distant objects, this time delay becomes even more dramatic. The light from the Andromeda Galaxy, our nearest galactic neighbor, has been traveling for over 2 million years to reach our eyes. When we look at Andromeda, we are seeing it as it existed when our earliest human ancestors were just learning to use tools. The most distant galaxies we can observe are showing us the universe as it was billions of years ago, when it was young and very different from today. This means that if a star exploded in a distant galaxy today, we would not know about it for millions or billions of years. The universe is vast beyond imagination, and the speed of light, fast as it is, still takes eons to carry information across cosmic distances. The speed of light also sets fundamental limits on communication and travel across cosmic distances. Even if we could build spacecraft that traveled at a significant fraction of light speed, journeys to nearby stars would still take years or decades. A journey to the center of our galaxy would take tens of thousands of years. Journeys to distant galaxies would take millions of lifetimes. The universe, it seems, has imposed a fundamental isolation on all its inhabitants. This isolation has shaped the entire history of life on Earth. Every living thing that has ever existed on our planet has been confined to this single world by the vast distances and the speed limit of light. We have evolved in cosmic solitude, unaware of what wonders or terrors might exist among the stars. Yet, as we will discover, this apparent limitation may not be the final word. Nature may have provided ways around this cosmic speed limit, hidden pathways through space and time that we are only beginning to understand. The universe is full of surprises, and the speed of light may be just the beginning of a much larger story. The year 1905 marked a turning point in human understanding of the universe. A young patent clerk working in Bern, Switzerland, published a paper that would forever change how we think about space, time, and the speed of light. His name was Albert Einstein, and his theory of special relativity would reveal that the constancy of light speed was not just a curious observation, but a fundamental principle that governs the very structure of reality itself. Einstein began with a simple but profound insight. He realized that the speed of light being constant for all observers was not a problem to be solved, but a truth to be embraced. Instead of asking why light behaves this way, he asked what this behavior tells us about the nature of space and time. The answer was revolutionary beyond anything anyone had imagined. According to Einstein's theory, space and time are not separate, independent entities as we experience them in our daily lives. Instead, they are woven together into a single fabric called space-time. This four-dimensional tapestry forms the stage upon which all events in the universe unfold. The speed of light is not just the speed at which light travels, it is the speed at which causality itself propagates through space-time. It is the speed at which cause and effect can spread from one point to another. This insight immediately explained why nothing can travel faster than light. If something could exceed the speed of light, it would be able to outrun causality itself. Effects could precede their causes. The logical order of events could be scrambled. The universe would become a place where consequences could happen before their origins. where the future could influence the past in ways that would create paradoxes and contradictions. Einstein's theory made several predictions that seemed impossible at the time, but have since been confirmed with extraordinary precision. The first prediction was time dilation. According to relativity, time does not flow at the same rate for everyone. If you could travel at speeds approaching the speed of light, time would slow down for you, relative to someone who remained stationary. This is not an illusion or a measurement error. Time literally passes more slowly for objects moving at high speeds. Imagine a twin who travels to a distant star at 99% the speed of light, while her sister remains on Earth. During the journey, the traveling twin experiences time, normally from her own perspective. Her heartbeat, her thoughts, her biological processes all proceed at their usual pace. But when she returns to Earth after what seems to her like just a few years, she discovers that decades have passed on her home planet. Her sister has aged many years, while she has aged only slightly. This is not science fiction. It is a consequence of the fundamental structure of space-time. Time dilation has been confirmed in countless experiments. Atomic clocks flown on airplanes run slightly slow compared to identical clocks left on the ground. Particles created in cosmic ray showers high in the atmosphere should decay long before reaching Earth's surface. But time dilation allows them to survive their journey because their internal clocks are running slow. Even the Global Positioning System satellites that provide navigation data to your phone must account for time dilation effects, or their measurements would be off by several kilometers. The second prediction of relativity is length contraction. Objects moving at high speeds actually become shorter in the direction of their motion. A spacecraft traveling at 90% the speed of light would appear to be compressed to less than half its original length as measured by a stationary observer. Again, this is not an optical illusion. The spacecraft is genuinely shorter. Space itself is compressed in the direction of motion. This compression of space and the slowing of time are intimately related. They are two aspects of the same underlying phenomenon, the warping of space-time by high-speed motion. As an object approaches the speed of light, space contracts and time dilates in exactly the right proportions to ensure that the speed of light remains constant for all observers. The third prediction is perhaps the most famous, the equivalence of mass and energy expressed in the equation E equals mc squared. This simple formula reveals that mass and energy are interchangeable. A small amount of mass can be converted into an enormous amount of energy, and energy can be converted back into mass. This is the principle that powers the sun and all other stars. It is also the principle that makes it impossible for objects with mass to reach the speed of light. As an object accelerates, its kinetic energy increases. But according to relativity, this additional energy manifests as additional mass. The faster the object moves, the more massive it becomes. This increasing mass makes it progressively harder to accelerate the object further. As the object approaches the speed of light, its mass approaches infinity, and the energy required to accelerate it any further also approaches infinity. This creates an insurmountable barrier. No finite amount of energy can accelerate an object with mass to the speed of light. The universe itself prevents this violation of the cosmic speed limit through the mechanism of increasing mass. It is as if the faster you try to go, the heavier you become, making it ever more difficult to go faster still. Only particles with zero mass, like photons, can travel at the speed of light. For these massless particles, traveling at light speed is not just possible, it is mandatory. They cannot exist at rest. They cannot travel slower than light. They are locked into perpetual motion at exactly the speed of light from the moment they are created until the moment they are destroyed. Einstein's theory also revealed something profound about simultaneity. Events that appear to happen at the same time for one observer may not be simultaneous for another observer moving at a different speed. This relativity of simultaneity means that there is no universal now that applies throughout the universe. The present moment is different for different observers depending on their motion through space-time. This has profound implications for our understanding of reality. If there is no universal now, then the future already exists in some sense, just as the past continues to exist. The universe becomes a four-dimensional block of space-time in which all events, past, present, and future, are equally real. We experience time as flowing because of our particular perspective, as conscious beings embedded within this four-dimensional structure. The theory of relativity also introduced the concept of reference frames. A reference frame is essentially a coordinate system used to describe the position and motion of objects. Einstein showed that the laws of physics must be the same in all reference frames that are moving at constant velocity relative to each other. This principle, called the principle of relativity, means that there is no absolute state of rest or absolute motion. Motion is always relative to something else. This principle has surprising consequences. If you are traveling in a smooth-moving train with the windows covered, there is no experiment you can perform inside the train that will tell you whether you are moving or stationary. The laws of physics work exactly the same way, regardless of your state of uniform motion. Only acceleration can be detected absolutely, not velocity. The constancy of the speed of light combined with the principle of relativity leads to all the strange effects we have discussed. Time dilation, length contraction, mass-energy equivalence, and the relativity of simultaneity all flow naturally from these two simple postulates. The mathematics of relativity, while complex in detail, is built upon this elegant foundation. One of the most remarkable aspects of Einstein's theory is how it unifies space and time into space-time. In our everyday experience, space and time seem completely different. Space has 3 dimensions: length, width, and height. Time has 1 dimension: duration. We can move freely through space but seem to move only forward through time. Relativity reveals that this separation is an illusion created by our limited perspective. In space-time, all objects, including you right now, are moving at the speed of light. This might seem impossible since you are sitting still, but you are moving through time at the rate of 1 second per second. Your total motion through space-time, combining your motion through space and your motion through time, always equals the speed of light. When you move faster through space, you automatically move slower through time, and vice versa. This 4-dimensional view of reality shows us that the speed of light is not just a speed limit for motion through space, it is the fundamental rate at which all things move through space-time itself. It is the heartbeat of the universe, the rhythm that governs all change and all existence. Yet, even as relativity established the speed of light as a universal constant and an ultimate speed limit, it also hinted at possibilities that might allow us to circumvent this limit in unexpected ways. The theory describes how space and time can be warped and curved. If space itself can be manipulated, perhaps the distance between 2 points can be shortened, or perhaps shortcuts through space-time can be created. These possibilities would not violate relativity because they would not involve traveling faster than light through space. Instead, they would involve altering the structure of space itself. The distinction is crucial and opens the door to concepts like warp drives and wormholes that we will explore in our journey ahead. Einstein's theory of relativity transformed our understanding of the universe and established the speed of light as the ultimate cosmic speed limit. But it also showed us that space and time are far more flexible and mysterious than we ever imagined. In this flexibility lies the potential for discoveries that might one day allow us to transcend the limitations imposed by the speed of light, not by breaking the rules of physics, but by finding new ways to play the game. In the realm of theoretical physics, few concepts capture the imagination quite like the warp drive. This is not merely the stuff of science fiction, but a serious scientific proposal that could, in principle, allow us to travel faster than light, without violating Einstein's theory of relativity. The key insight is elegantly simple. Instead of moving through space faster than light, we manipulate space itself to bring our destination closer to us. The concept of a warp drive was first mathematically formulated in 1994 by Mexican physicist Miguel Alcubierre. His groundbreaking paper, published in the journal Classical and Quantum Gravity, showed that Einstein's field equations, the very equations that establish the speed of light as a cosmic speed limit, also permit the existence of a space-time geometry that could enable faster than light travel. Alcubierre's warp drive works by creating a bubble of curved space-time around a spacecraft. This bubble contracts space in front of the ship and expands space behind it. The ship itself never actually moves through space faster than light. Instead, space moves around the ship, carrying it along like a surfer riding a wave. From the perspective of someone inside the bubble, the journey is smooth and comfortable. From the perspective of an outside observer, the bubble and everything inside it appears to move faster than light. To understand how this works, imagine space as a vast, flexible sheet. Normally, to travel from one point on this sheet to another distant point, you would have to move across the surface at whatever speed you can manage. But what if you could grab the sheet and stretch it, bringing the distant point closer to your starting position? What if you could then compress the sheet behind you, pushing your starting point further away? This is essentially what an Alcubierre warp drive does to the fabric of space-time itself. The mathematics behind this concept are rooted in Einstein's theory of general relativity, which describes gravity not as a force, but as a curvature of space-time. Massive objects like stars and planets warp the geometry of space-time around them, and this warping is what we experience as gravitational attraction. Alcubierre showed that it is theoretically possible to create a different kind of space-time curvature, one that propels objects through space rather than attracting them together. In the Alcubierre metric, as physicists call this mathematical description of curved space-time, the region of space in front of the spacecraft contracts, while the region behind it expands. The spacecraft rides in a flat region of space-time between these two curved regions. This flat region, often called the warp bubble, moves through space at whatever speed is desired, potentially many times faster than the speed of light. From inside the bubble, the experience would be remarkable. The passengers would feel no acceleration forces, no sense of movement at all. They would be in free fall through perfectly flat space-time, feeling weightless and comfortable. Time would pass normally for them. They could look out windows and see the universe rushing past at incredible speeds, but they themselves would be at rest relative to their immediate space-time environment. The energy requirements for creating such a warp bubble are, however, staggering. Alcubierre's original calculations suggested that the energy needed would be equivalent to the mass energy of the entire observable universe. This is clearly far beyond anything we could hope to achieve with any conceivable technology. The energy required is not just large, it is incomprehensibly vast, many orders of magnitude greater than the total energy output of our Sun over its entire 10 billion-year lifetime. Moreover, the type of energy required is not ordinary matter or energy. The Alcubierre drive requires what physicists call exotic matter, specifically matter with negative energy density. This is matter that weighs less than nothing, matter that has the opposite gravitational effect of normal matter. Instead of attracting other objects, exotic matter would repel them. Instead of curving space-time inward, it would curve space-time outward. Exotic matter is not just rare or difficult to create. It may not exist at all. No one has ever observed matter with negative energy density in nature. Some quantum effects can create regions of negative energy density on extremely small scales and for extremely brief periods, but these effects are far too weak and fleeting to be useful for macroscopic applications like warp drives. However, the story does not end with these daunting challenges. In the years since Alcubierre's original paper, physicists have found ways to dramatically reduce the energy requirements for warp drives. In 1999, Chris van den Broek showed that by changing the shape of the warp bubble, the energy requirements could be reduced from the mass of the observable universe to something on the order of the mass of the Sun. This is still an enormous amount of energy, but it represents an improvement of many orders of magnitude. More recent work has pushed these energy requirements even lower. Some proposals suggest that the energy needed might be reduced to the mass of a large asteroid, or even the mass of a small spacecraft. While these amounts of energy are still far beyond our current technological capabilities, they are at least within the realm of what an advanced civilization might potentially achieve. The key insight behind these improvements is that the shape and structure of the warp bubble can be optimized to minimize energy requirements. Instead of a large, thick bubble surrounding the entire spacecraft, researchers have proposed thin, carefully shaped bubbles that achieve the same effect with far less exotic matter. Some designs even suggest that the bubble need not completely surround the spacecraft, but could be a partial bubble or a series of smaller bubbles arranged in specific configurations. Another promising development is the discovery that certain configurations of warp bubbles might be able to use naturally occurring quantum fluctuations in spacetime, rather than requiring large amounts of artificially created exotic matter. The quantum vacuum, empty space itself, is filled with virtual particles that pop into existence and disappear again in extremely brief time intervals. These quantum fluctuations create tiny amounts of negative energy density throughout space. A sufficiently clever warp drive design might be able to harness and amplify these natural fluctuations. The concept of manipulating space-time for propulsion is not limited to the Alcubierre drive. Physicists have proposed numerous variations and alternatives, each with its own advantages and challenges. Some designs focus on creating localized distortions in space-time that can be surfed like waves. Others propose using the expansion of space itself as a propulsion mechanism, similar to how the universe expands and carries distant galaxies away from us faster than light. One particularly intriguing variation is the idea of a warp drive that does not require exotic matter at all, but instead uses the interplay between ordinary matter and the geometry of space-time in clever ways. These designs are still highly speculative and face their own formidable challenges, but they offer hope that faster-than-light travel might be possible without requiring matter that may not exist. The implications of successful warp drive technology would be profound beyond imagination. Journeys that would take thousands of years with conventional propulsion could be completed in days or weeks. The nearest stars would become as accessible as the nearest cities. Humanity could spread throughout the galaxy, establishing colonies and exploring worlds that are currently forever beyond our reach. Such technology would also revolutionize our understanding of physics and our place in the universe. It would demonstrate that the apparent limitations imposed by the speed of light are not absolute barriers, but challenges to be overcome through deeper understanding and more sophisticated technology. It would open up entirely new fields of research into the manipulation of space-time and the fundamental structure of reality. Yet the challenges facing warp drive development remain enormous. Beyond the energy and exotic matter requirements, there are numerous other technical and theoretical obstacles. The creation and control of the warp bubble would require technologies far beyond anything we currently possess. The navigation and stability of a warp drive spacecraft would present unique challenges, as would communication with the outside universe while traveling faster than light. There are also potential dangers associated with warp drive technology. The energy densities involved are so extreme that small errors could have catastrophic consequences. The interaction between the warp bubble and normal matter could produce dangerous radiation or other harmful effects. Some theoretical studies suggest that the collapse of a warp bubble could release devastating amounts of energy, potentially destroying anything in the vicinity. Despite these challenges, research into warp drive physics continues to advance. Scientists around the world are working to better understand the fundamental principles involved, to find ways to reduce energy requirements further, and to explore alternative approaches to faster-than-light travel. While we are still very far from building an actual warp drive, our understanding of the underlying physics grows deeper with each passing year. The pursuit of warp drive technology represents humanity at its most ambitious. It embodies our refusal to accept limitations, our determination to explore and discover, and our faith that the universe holds secrets yet to be unlocked. Whether or not we will ever build a working warp drive remains an open question, but the very fact that such devices are theoretically possible keeps alive our dreams of traveling to the stars and exploring the vast cosmos that surrounds us. Deep within the mathematical structure of Einstein's theory of general relativity lies one of the most fascinating and mysterious possibilities in all of physics: the wormhole. These hypothetical tunnels through space-time could potentially connect distant regions of the universe, allowing travel between them in far less time than light would take to make the same journey through normal space. Unlike warp drives, which manipulate space around a spacecraft, wormholes would provide actual shortcuts through the fabric of space-time itself. The concept of wormholes emerged from the mathematical solutions to Einstein's field equations discovered by physicists Karl Schwarzschild and Ludwig Flamm in the early 20th century. While studying the geometry of space-time around massive objects, they found that the equations permitted strange configurations where space could be curved so severely that it essentially folds back on itself, creating a bridge or tunnel between two different regions of space-time. To visualize a wormhole, imagine a vast sheet of paper representing the two-dimensional surface of space. If you want to travel from one point on this sheet to another distant point, you would normally have to travel along the surface of the paper, covering the entire distance between the 2 points. But what if you could fold the paper so that the 2 points touch, then poke a hole through both points where they meet? You would have created a shortcut, a tunnel that allows you to travel from one point to the other without covering all the distance in between. This is essentially what a wormhole does in the three-dimensional space we inhabit, plus the additional dimension of time. The mathematics of wormholes reveals several different types of these space-time tunnels. The simplest type is called an Einstein-Rosen bridge, named after Albert Einstein and Nathan Rosen, who first studied its properties in detail in 1935. This type of wormhole connects two different regions of space-time through a narrow throat or bottleneck. From the outside, each mouth of the wormhole might appear as a spherical surface hanging in space, but this surface would be a gateway to another part of the universe entirely. However, Einstein-Rosen bridges have a fundamental flaw that makes them useless for travel. These wormholes are inherently unstable and would collapse faster than anything, even light, could travel through them. The geometry of space-time around the wormhole throat is so precarious that the slightest disturbance, even the presence of a single photon trying to pass through, would cause the entire structure to pinch off and disappear. It would be like trying to travel through a tunnel that collapses the moment you step inside. This instability problem led physicists to investigate whether there might be ways to stabilize wormholes and keep them open long enough for objects to pass through. The solution they discovered requires something we encountered in our discussion of warp drives: exotic matter with negative energy density. Just as warp drives need exotic matter to compress and expand space-time, traversable wormholes need exotic matter to prevent their collapse. The exotic matter would need to be threaded through the wormhole throat, creating what physicists call a stress-energy tensor that violates the null energy condition. In simpler terms, this means the matter in the wormhole throat would need to have properties that are the opposite of normal matter. Instead of having positive energy density and pressure, it would need negative energy density and negative pressure. This exotic matter would push outward on the walls of the wormhole throat, preventing them from collapsing inward. The amount of exotic matter required to stabilize a wormhole depends on the size of the wormhole and the strength of its gravitational field. For a wormhole large enough to allow a spacecraft to pass through, the exotic matter requirements are enormous, potentially requiring more negative energy than exists in the entire observable universe. Once again, we encounter the same fundamental challenge that faces warp drive technology: the need for vast amounts of a type of matter that may not exist in nature. Despite these challenges, physicists have continued to explore the theoretical properties of wormholes and search for ways to make them more practical. One promising approach involves the use of quantum effects near the wormhole throat. Quantum mechanics tells us that empty space is not truly empty, but is filled with quantum fluctuations that create temporary pairs of virtual particles. These fluctuations can sometimes produce small amounts of negative energy density, exactly what is needed to stabilize a wormhole. Some theoretical models suggest that advanced civilizations might be able to harness and amplify these quantum fluctuations to create and maintain traversable wormholes. The process would require extraordinarily sophisticated technology capable of manipulating quantum fields on macroscopic scales, but it would not require the creation of exotic matter from nothing. Instead, it would involve the careful arrangement and concentration of naturally occurring quantum effects. Another intriguing possibility is that wormholes might form naturally under certain extreme conditions in the universe. Some physicists have speculated that wormholes could be created during the violent processes that occur during the formation of black holes, or during the earliest moments of the universe, when space-time itself was in a state of extreme turbulence. These naturally occurring wormholes might then persist throughout cosmic history, waiting to be discovered and potentially utilized by sufficiently advanced civilizations. The search for natural wormholes has become an active area of research in theoretical astrophysics. Scientists have proposed various observational signatures that might indicate the presence of a wormhole mouth in our cosmic neighborhood. These signatures include unusual gravitational lensing effects, where light from distant objects would be bent and focused in ways that cannot be explained by known massive objects. Wormhole mouths might also produce distinctive patterns of radiation as matter falls into them or emerges from them. One of the most fascinating aspects of traversable wormholes is their potential relationship with time travel. According to general relativity, if you could create a wormhole and then move one mouth of it at high speed relative to the other mouth, time dilation effects would cause the two mouths to experience time at different rates. This could create a time machine, allowing travel not just to distant places but to different times as well. The implications of such time travel capabilities are mind-bending and raise profound questions about the nature of causality and free will. Could you travel back in time and change the past? What would happen if you prevented your own birth? These paradoxes have led some physicists to propose that the laws of physics might contain hidden protections against time travel, preventing the formation of closed time-like curves that could lead to logical contradictions. The study of wormholes has also led to surprising connections with other areas of physics, particularly quantum mechanics and information theory. Some researchers have proposed that quantum entanglement, the mysterious connection between particles that we will explore in a later chapter, might be fundamentally related to microscopic wormholes connecting the entangled particles. This idea, known as the ADS-CFT correspondence, suggests that the geometry of space-time and the information content of quantum systems might be intimately connected in ways we are only beginning to understand. Recent advances in theoretical physics have also revealed new types of wormhole solutions to Einstein's equations. Some of these solutions require less exotic matter than traditional wormholes, while others might be stabilized by effects other than exotic matter entirely. Researchers have discovered wormhole solutions that are supported by electromagnetic fields, by the rotation of space-time itself, and by the interaction between gravity and quantum fields. The practical challenges of constructing and using wormholes remain formidable. Even if we could create the exotic matter needed to stabilize a wormhole, we would still need to solve the engineering problems of how to create the wormhole in the first place, how to control its size and location, and how to ensure safe passage through the tunnel. The forces involved would be gravitational fields so strong that they could tear apart any known material, and the energy requirements would dwarf anything in human experience. Navigation through a wormhole would present unique challenges unlike anything encountered in normal space travel. The geometry of space-time inside the wormhole throat would be severely curved, potentially creating tidal forces that could stretch and compress objects passing through. The passage might also involve exposure to intense radiation fields or exotic forms of matter and energy that could be harmful to living beings. Communication across a wormhole would also be problematic. Radio signals and other forms of electromagnetic radiation traveling through normal space would take the long way around, potentially arriving long after travelers who took the wormhole shortcut. This could create situations where effects arrive before their causes, at least from the perspective of observers using normal communication channels. Despite these challenges, the theoretical possibility of wormholes continues to inspire scientists and capture the public imagination. The idea that there might be hidden doorways scattered throughout the universe, connecting distant worlds and civilizations, speaks to our deepest longings for exploration and discovery. It suggests that the vast emptiness of space between the stars might not be the insurmountable barrier it appears to be. Some scientists have speculated that sufficiently advanced civilizations might use wormholes to create transportation networks spanning entire galaxies. Such networks could allow rapid travel and communication across cosmic distances, enabling the development of truly galactic civilizations. The construction and maintenance of such networks would require technology so advanced that it would seem like magic to us, but it would not necessarily violate any known laws of physics. The search for evidence of such wormhole networks has become part of the broader search for extraterrestrial intelligence. Scientists look for unusual patterns in the distribution of matter and energy in the universe that might indicate artificial manipulation of space-time. They search for signatures of exotic matter or unusual gravitational effects that might reveal the presence of wormhole mouths or other advanced space-time engineering projects. Whether natural or artificial wormholes exist remains an open question. The theoretical foundation for their existence is solid, rooted in the well-tested mathematics of general relativity. The practical challenges of creating and using them are enormous, but they are challenges of engineering and energy, rather than fundamental violations of physical law. Like warp drives, wormholes represent a potential pathway to faster-than-light travel that does not require us to break the speed of light, but instead to transcend it through deeper manipulation of space-time itself. In the strange and wonderful world of quantum mechanics, particles behave in ways that defy our everyday understanding of reality. They can exist in multiple states simultaneously, tunnel through barriers that should be impenetrable, and most mysteriously of all, they can become entangled with other particles in ways that create instantaneous connections across vast distances. This phenomenon, known as quantum entanglement, might hold the key to understanding how information, and perhaps even matter, could travel faster than light. Quantum entanglement was first described by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935. They were troubled by what the mathematics of quantum mechanics seemed to imply about the nature of reality. According to the theory, two particles could become entangled in such a way that measuring the properties of one particle would instantly determine the properties of the other, regardless of how far apart they might be. Einstein famously called this spooky action at a distance and believed it revealed a fundamental flaw in quantum mechanics. To understand entanglement, imagine two coins that have been specially prepared so that they are forever linked. When you flip one coin and it comes up heads, the other coin, no matter where it is in the universe, instantly becomes tails. When the first coin shows tails, the second instantly becomes heads. The coins are not communicating with each other in any ordinary sense. There is no signal traveling between them. Instead, they share a single quantum state that encompasses both particles simultaneously. This is precisely what happens with entangled particles. When two particles become entangled, they lose their individual identities and become part of a single quantum system. The particles might be photons with entangled polarizations, electrons with entangled spins, or atoms with entangled energy states. Regardless of the specific property that is entangled, the key feature is always the same. Measuring one particle instantly affects the state of its entangled partner. The instantaneous nature of this connection troubled Einstein because it seemed to violate the principle that nothing can travel faster than light. If measuring one particle instantly affects another particle on the other side of the galaxy, how is this different from sending information faster than light? Einstein believed that quantum mechanics must be incomplete, that there must be hidden variables that predetermined the outcomes of measurements and eliminated the need for instantaneous connections. For decades, the question of whether quantum entanglement really involved faster than light connections remained a matter of philosophical debate. The effects of entanglement could be observed in laboratory experiments, but it was unclear whether they represented genuine instantaneous connections or simply revealed pre-existing correlations between the particles. This changed in 1964 when physicist John Stuart Bell devised a mathematical test that could distinguish between these two possibilities. Bell's theorem showed that if particles had predetermined properties that accounted for their correlations, then certain statistical patterns would emerge when many measurements were performed. But if quantum entanglement involved genuine instantaneous connections, different statistical patterns would appear. Experiments could therefore determine which view of reality was correct by carefully measuring these statistical patterns. The first definitive tests of Bell's theorem were performed in the 1970s and early 1980s by physicists such as John Clauser, Alain Aspect, and others. The results were unambiguous. The statistical patterns matched exactly what quantum mechanics predicted for genuine entanglement. The correlations between entangled particles could not be explained by any theory involving predetermined properties or hidden variables. The instantaneous connections were real. These experimental confirmations of quantum entanglement earned Alain Aspect, John Clauser, and Anton Zeilinger the Nobel Prize in Physics in 2022. Their work definitively established that entangled particles really do share instantaneous connections that transcend the normal limitations of space and time. The universe, it seems, is even stranger than Einstein had imagined. But if entangled particles can affect each other instantaneously across any distance, why can we not use this phenomenon to send information faster than light? The answer lies in the subtle nature of quantum measurements. When you measure the state of an entangled particle, you get a random result. You cannot control what result you will obtain. You might measure the spin of an electron and find it pointing up, or you might find it pointing down, but you cannot force it to be in either state. The randomness of quantum measurements means that even though the measurement of one entangled particle instantly affects its partner, no information is actually transmitted. The person measuring the second particle sees only random results. They have no way of knowing whether their particle's state was determined by its own random quantum behavior or by a measurement performed on its entangled partner somewhere else in the universe. This limitation led many physicists to conclude that quantum entanglement, while mysterious and fascinating, could never be used for faster-than-light communication or travel. the phenomenon seemed to be forever relegated to the realm of fundamental physics research, with no practical applications for overcoming the cosmic speed limit. However, some researchers have proposed more subtle ways that quantum entanglement might enable faster-than-light effects. One possibility involves quantum teleportation, a process discovered in 1993 that allows the complete quantum state of one particle to be transferred to another particle using entanglement and classical communication. In quantum teleportation, the original particle is destroyed in the process of measurement, while its entangled partner at a distant location takes on the exact quantum state that the original particle possessed. Quantum teleportation has been successfully demonstrated in numerous laboratory experiments and is now used in practical applications such as quantum cryptography and quantum computing. However, the process still requires classical communication to complete the transfer of information, and this classical communication cannot travel faster than light. The quantum state information is transferred instantaneously through entanglement, but additional classical information must be sent by conventional means to reconstruct the original quantum state at the destination. Some physicists have speculated about ways to enhance or amplify quantum entanglement effects to overcome the usual limitations. One possibility involves the use of many entangled particles working together in coordinated ways. Just as a laser amplifies the effects of individual photons to create intense beams of coherent light, it might be possible to amplify entanglement effects to create macroscopic phenomena that could be used for communication or transportation. Another intriguing possibility involves the relationship between quantum entanglement and the geometry of spacetime itself. Some theoretical models suggest that entangled particles might be connected by microscopic wormholes that exist at the quantum level. If this is true, then the instantaneous connections of quantum entanglement might actually involve information traveling through these quantum wormholes, rather than across normal space. This would provide a physical mechanism for the mysterious correlations without requiring faster-than-light signaling through ordinary spacetime. The idea that quantum entanglement might be related to microscopic wormholes has led to exciting new research directions in theoretical physics. Some scientists have proposed that the emergence of spacetime itself might be fundamentally connected to quantum entanglement. In this view, the three-dimensional space we experience might be an emergent property arising from the entanglement patterns of more fundamental quantum entities existing in higher dimensional spaces. This perspective suggests that space and time are not fundamental features of reality, but rather statistical patterns that emerge from underlying quantum information. If this is correct, then manipulating quantum entanglement might provide a way to manipulate the structure of spacetime itself. Advanced civilizations might be able to use quantum entanglement to create artificial wormholes, modify the topology of space, or even create entirely new regions of spacetime. Recent experiments have pushed the boundaries of quantum entanglement to ever larger scales and greater distances. Scientists have successfully entangled particles separated by hundreds of kilometers using satellite links. They have entangled increasingly complex systems involving multiple particles and multiple properties. Some experiments have even claimed to observe entanglement effects in systems containing billions of particles, suggesting that quantum effects might persist even at macroscopic scales under the right conditions. The field of quantum biology has revealed that entanglement might play important roles in biological systems. Some researchers have proposed that quantum entanglement might be involved in photosynthesis, allowing plants to transfer energy with remarkable efficiency. Others have suggested that quantum effects might be important in bird navigation, allowing birds to sense magnetic fields through quantum entanglement in their retinas. If quantum effects can operate in warm, noisy biological systems, it suggests that entanglement might be more robust and versatile than previously thought. These discoveries have led some scientists to speculate about the possibility of biological systems that could harness quantum entanglement for enhanced capabilities. Could evolution produce organisms that use quantum entanglement to communicate over long distances or to navigate through space? Could conscious beings develop the ability to directly manipulate quantum states through mental intention? While these ideas remain highly speculative, they illustrate the profound implications that quantum entanglement might have for our understanding of life and consciousness. The practical applications of quantum entanglement continue to expand rapidly. Quantum computers use entanglement to perform calculations that are impossible with classical computers. Quantum cryptography uses entanglement to create unbreakable codes for secure communication. Quantum sensors use entanglement to achieve unprecedented precision in measuring time, distance, and other physical quantities. These technologies are already beginning to transform fields ranging from finance to medicine to national security. Looking toward the future, some researchers envision quantum technologies that could revolutionize transportation and communication. Quantum computers might eventually become powerful enough to simulate the behavior of space-time itself, allowing us to discover new ways to manipulate gravity and geometry. Quantum communication networks might enable instantaneous coordination of activities across vast distances, even if they cannot transmit information faster than light. Quantum sensors might detect gravitational waves, dark matter, or other exotic phenomena that could reveal new physics beyond our current understanding. The mystery of quantum entanglement continues to deepen as our experimental capabilities advance. Each new discovery reveals additional layers of strangeness and possibility. While we still do not fully understand how entanglement works or what its ultimate implications might be, we know that it represents a fundamental feature of reality that transcends our everyday experience of space and time. Perhaps most intriguingly, quantum entanglement suggests that the universe is far more interconnected than classical physics would suggest. Every particle that has ever interacted with another particle remains forever entangled with it in some subtle way. This creates a vast web of quantum correlations spanning the entire cosmos, a network of connections that links every part of the universe to every other part through the mysterious realm of quantum mechanics. Whether this quantum web of connections could ever be harnessed for faster-than-light travel or communication remains an open question. The challenges are formidable, but the potential rewards are extraordinary. In the strange world of quantum mechanics, where particles can exist in multiple states simultaneously and distant objects can share instantaneous connections, perhaps even the speed of light is not an absolute barrier, but simply another boundary waiting to be transcended through deeper understanding of the quantum nature of reality. In the realm of theoretical physics, there exists a class of hypothetical particles that challenge our understanding of the cosmic speed limit in the most direct way possible. These particles, called tachyons, are theorized to always travel faster than light, never slower. Unlike the space-time manipulation of warp drives or the quantum mysteries of entanglement, tachyons would achieve faster than light travel through the simple expedient of having been born that way, created by the universe itself to forever race through space at superluminal speeds. The concept of tachyons emerged from a careful examination of Einstein's equations of special relativity. While these equations forbid ordinary matter from reaching or exceeding the speed of light, they do not explicitly forbid the existence of particles that are already traveling faster than light. The mathematical framework of relativity actually accommodates three distinct classes of particles: tardions, which always travel slower than light; luxons, which always travel at exactly the speed of light; and tachyons, which would always travel faster than light. The name tachyon comes from the Greek word tachys, meaning swift or fast. It was coined in 1967 by physicist Gerald Feinberg, who conducted the first systematic study of these hypothetical, faster-than-light particles. Feinberg showed that if tachyons exist, they would have several remarkable and counterintuitive properties that set them apart from ordinary matter in fundamental ways. The most striking property of tachyons is that they cannot be slowed down to the speed of light, much less brought to rest. Just as ordinary particles with mass require infinite energy to reach the speed of light, tachyons would require infinite energy to slow down to the speed of light. This creates an insurmountable barrier that separates the world of ordinary matter from the hypothetical realm of tachyons. Normal matter lives forever below the speed of light, while tachyons would live forever above it, with the speed of light acting as an impermeable boundary between these two realms. Another strange property of tachyons involves their relationship between energy and speed. For ordinary particles, adding energy makes them go faster, but for tachyons, the relationship is reversed. The more energy a tachyon has, the slower it goes, though it can never slow down enough to reach the speed of light. Conversely, as a tachyon loses energy, it speeds up. A tachyon with zero energy would travel at infinite speed, appearing everywhere in the universe simultaneously. This inverse relationship between energy and speed leads to even more bizarre consequences when we consider what would happen if tachyons could interact with ordinary matter. If a tachyon were to give up some of its energy to a normal particle, the tachyon would speed up while the normal particle would gain energy and speed up as well. This creates the possibility of runaway processes, where interactions between tachyons and normal matter could lead to unlimited acceleration and energy production, potentially violating conservation of energy. The mathematical description of tachyons requires them to have imaginary mass. This does not mean that their mass is somehow unreal or fictional, but rather that when you calculate their mass using Einstein's equations, you get a number that involves the square root of -1. This imaginary mass is what allows tachyons to travel faster than light, while still satisfying the mathematical constraints of special relativity. When tachyons move through space, they would create a wake of electromagnetic radiation, similar to the sonic boom created by aircraft traveling faster than the speed of sound. This electromagnetic wake, called Cherenkov radiation, would drain energy from the tachyon, causing it to speed up rather than slow down. This creates another paradox. The natural process that should dissipate a tachyon's energy actually makes it go faster, potentially leading to unlimited acceleration. The time travel implications of tachyons are particularly mind-bending. Because they travel faster than light, tachyons moving from one point to another could arrive before light carrying information about their departure has had time to propagate. This means that tachyons could potentially carry information into the past, creating the possibility of communicating with earlier times or even influencing past events. Consider a simple thought experiment involving tachyon communication. Imagine that Earth and a distant planet both have tachyon transmitters and receivers. If someone on Earth sends a tachyon message to the distant planet, the message arrives almost instantly. But due to the relativistic effects of motion, an observer on the distant planet who is moving relative to Earth might receive the message before it was sent from Earth's perspective. If this observer then sends a reply back to Earth, that reply could arrive before the original message was sent, creating a causal loop where effects precede their causes. These causality violations are so problematic that many physicists believe they provide strong evidence against the existence of tachyons. If tachyons could carry information faster than light, they would undermine the logical structure of cause and effect that underlies all of physics. Events could influence their own past, creating paradoxes that seem to make the universe logically inconsistent. However, some researchers have proposed ways that tachyons might exist without creating causality paradoxes. One possibility is that tachyons cannot carry information at all. They might be detectable as particles, but their properties might be completely random and uncontrollable, making them useless for communication. Another possibility is that the universe has built-in protections against causality violations, mechanisms that prevent tachyons from being used to send information into the past, even if they can travel faster than light. The search for experimental evidence of tachyons has been ongoing for decades, but no confirmed detection has ever been made. Several experiments have claimed to observe faster than light particles, but these results have either been retracted due to experimental errors or have failed to be reproduced by other research groups. The most famous case occurred in 2011, when researchers at the Opera experiment in Italy reported that neutrinos appeared to travel faster than light. This result generated enormous excitement and media attention, but was later found to be due to a loose fiber optic cable that introduced timing errors into the measurements. Despite the lack of experimental evidence, theoretical interest in tachyons continues. Some models of particle physics include tachyonic fields that play important roles in the fundamental structure of matter and energy. In these models, tachyons are not particles that can be directly observed, but rather mathematical objects that describe the behavior of quantum fields in certain circumstances. One area where tachyonic concepts appear is in the theory of cosmic inflation, which describes the rapid expansion of space that occurred in the earliest moments after the Big Bang. Some models of inflation involve scalar fields that have tachyonic properties, meaning they have negative kinetic energy and exhibit the inverse relationship between energy and speed that characterizes tachyons. These tachyonic fields could drive the exponential expansion of space without violating causality because they describe the behavior of space-time itself rather than particles moving through space-time. Tachyons also appear in certain versions of string theory. the ambitious attempt to unify all the fundamental forces of physics into a single theoretical framework. In string theory, tachyonic modes can arise in the vibrations of fundamental strings, potentially indicating instabilities in the theory that must be resolved through additional physical mechanisms. Some researchers have proposed that these tachyonic instabilities might be features rather than bugs, representing new phases of matter or new types of physical phenomena that we have not yet discovered. The study of tachyons has also led to insights into the nature of causality and information in physics. Even if tachyons do not exist as real particles, the theoretical investigation of their properties has deepened our understanding of why the speed of light serves as a cosmic speed limit and what would happen if that limit could be violated. This understanding has applications in many areas of physics, from the study of black holes to the development of quantum field theory. Some researchers have proposed that tachyons might exist in parallel universes or higher dimensional spaces that are normally inaccessible to us. In these scenarios, tachyons would not violate causality in our three-dimensional world because they would be confined to spaces with different causal structures. Occasionally, these tachyons might briefly interact with our universe, potentially explaining some unexplained phenomena in particle physics or cosmology. The possibility that tachyons might be associated with consciousness or mental phenomena has also been explored by some researchers, though these ideas remain highly speculative and controversial. Some theories propose that thoughts or intentions might involve tachyonic processes that allow mental events to influence physical reality in ways that transcend normal causal limitations. While these ideas lack experimental support, they illustrate the profound implications that faster-than-light particles could have for our understanding of mind and matter. Recent developments in theoretical physics have suggested new ways that tachyon-like phenomena might manifest without creating causality paradoxes. Some models propose that apparent faster-than-light propagation could occur through the collective behavior of many particles or fields, even if individual particles never exceed the speed of light. Others suggest that quantum entanglement or other quantum mechanical effects might create correlations that appear tachyonic without actually involving faster-than-light signaling. The search for tachyons continues to motivate experimental research in particle physics and cosmology. Scientists look for signatures of faster-than-light particles in cosmic ray showers, in the decay products of high-energy particle collisions, and in the radiation from distant astronomical objects. While no definitive evidence has been found, the possibility remains that future experiments with greater sensitivity or new detection techniques might finally reveal the existence of these elusive, faster-than-light particles. Whether tachyons exist in nature remains one of the great open questions in physics. Their existence would revolutionize our understanding of space, time, and causality, potentially opening up new realms of physics beyond our current comprehension. Their non-existence would confirm our current understanding of relativity and the fundamental role of the speed of light as a cosmic speed limit. Either way, the theoretical study of tachyons continues to provide valuable insights into the deepest principles that govern our universe. As we drift deeper into our exploration of the cosmic speed limit, a provocative question emerges from the shadows of modern physics. What if we are already moving faster than light, but we simply do not recognize it? What if the universe itself is filled with phenomena that routinely exceed the speed of light, hidden in plain sight by our limited understanding of space, time, and the true nature of reality? This possibility is not as far-fetched as it might initially seem. The expansion of the universe itself provides a compelling example of faster-than-light motion that occurs all around us every moment of every day. When we look out into the depths of space, we observe galaxies racing away from us at tremendous speeds. The most distant galaxies we can detect are receding from us at velocities that exceed the speed of light by substantial margins. This cosmic expansion does not violate Einstein's theory of relativity, because the galaxies themselves are not moving through space faster than light. Instead, space itself is expanding, carrying the galaxies along with it like leaves, floating on the surface of a rapidly inflating balloon. The galaxies remain at rest relative to their local space-time, but the expansion of space between us and them creates the appearance of faster-than-light recession velocities. The implications of this cosmic expansion are profound. It means that there are regions of the universe that are moving away from us so rapidly that light from those regions will never be able to reach us, no matter how long we wait. These regions exist beyond what cosmologists call the cosmic event horizon, a boundary that separates the observable universe from the unobservable universe. As the expansion of space continues to accelerate, this horizon will continue to shrink, eventually cutting us off from more and more of the cosmos. But cosmic expansion is just one example of faster-than-light phenomena that may already surround us. Consider the mysterious substance known as dark matter, which makes up approximately 27% of all matter and energy in the universe. Dark matter interacts with ordinary matter only through gravity, making it essentially invisible to all our normal methods of detection. We know it exists because of its gravitational effects on visible matter, but we have no idea what it actually is or how it behaves. Some theoretical models suggest that dark matter particles might travel faster than light under certain circumstances. These particles would exist in a shadow realm parallel to our own, interacting with our universe only through gravitational forces. If dark matter can indeed exceed the speed of light, then faster-than-light matter might be streaming through your body right now, passing through the Earth and everything on it without leaving any trace of its passage except subtle gravitational effects. The phenomenon of quantum tunneling provides another intriguing example of apparently faster-than-light behavior. When particles encounter energy barriers that they should not have enough energy to overcome, quantum mechanics allows them to spontaneously appear on the other side of the barrier, as if they had magically teleported through it. This process happens instantaneously, with no time delay between the particle disappearing on one side of the barrier and appearing on the other side. Experiments have shown that the time required for quantum tunneling appears to be zero, regardless of the thickness of the barrier the particle tunnels through. This suggests that particles can traverse arbitrary distances instantaneously during the tunneling process, effectively traveling at infinite speed. While the interpretation of these experiments remains controversial, they hint at the possibility that nature routinely employs faster-than-light transport mechanisms at the quantum level. The behavior of quantum fields themselves might also involve faster-than-light propagation under certain circumstances. Quantum field theory describes all particles as excitations in underlying fields that permeate all of space. These fields can support various types of waves and disturbances, some of which might propagate faster than light, without carrying information or violating causality. Virtual particles, the ephemeral quantum fluctuations that pop in and out of existence throughout empty space, might also exhibit faster-than-light behavior. These particles exist for such brief periods that they are not subject to the normal energy momentum constraints that govern real particles. Some theoretical calculations suggest that virtual particles can propagate faster than light during their brief existence, contributing to various quantum phenomena that we observe in laboratory experiments. Recent discoveries in neutrino physics have revealed that these elusive particles exhibit behavior that challenges our understanding of the speed of light barrier. Neutrinos are nearly massless particles that interact very weakly with ordinary matter, allowing them to pass through entire planets as if they were not there. For many years, neutrinos were thought to be exactly massless and therefore required to travel at exactly the speed of light. However, experiments have now confirmed that neutrinos do have small but non-zero masses, which means they should travel slightly slower than light. Yet some experimental results have suggested that neutrinos might sometimes appear to travel faster than expected, though these results remain controversial and have not been definitively confirmed. The behavior of neutrinos in extreme environments like the cores of collapsing stars or the intense magnetic fields around neutron stars might involve physical processes that we do not yet understand. The phenomenon of entanglement, which we explored in an earlier chapter, represents perhaps the most direct evidence that the universe routinely employs faster-than-light connections. When entangled particles are separated by vast distances and one particle is measured, the state of its partner is instantly determined, regardless of the distance between them. This instantaneous correlation occurs faster than light could travel between the particles, suggesting that information or influence can propagate through quantum channels that transcend normal space-time limitations. While entanglement cannot be used to send controllable messages faster than light, it demonstrates that the universe is already permeated with faster-than-light correlations at the quantum level. Every interaction between particles creates entanglements that persist even when the particles are separated by cosmic distances. This creates a vast web of quantum correlations that spans the entire universe. connecting every part of the cosmos to every other part through channels that operate outside the normal constraints of space and time. The study of black holes has revealed additional phenomena that might involve faster-than-light behavior. When matter falls into a black hole, it appears to an outside observer to slow down and freeze at the event horizon, the boundary beyond which nothing can escape. However, from the perspective of the infalling matter, the journey continues normally, with the matter crossing the event horizon and falling toward the singularity at the center of the black hole. This difference in perspectives creates puzzles about what happens to information that falls into black holes. Some theories propose that information might be transferred out of black holes through quantum entanglement channels that operate faster than light. Others suggest that the event horizons of black holes might not be the impermeable barriers they appear to be, but rather dynamic boundaries that can emit information through processes we do not yet understand. The phenomenon of Hawking radiation, predicted by Stephen Hawking in 1974, suggests that black holes actually emit radiation and slowly evaporate over time. The mechanism behind this radiation involves quantum fluctuations near the event horizon that separate virtual particle pairs, with one particle falling into the black hole while the other escapes. Some aspects of this process might involve faster-than-light correlations between the escaping radiation and the information trapped inside the black hole. Recent developments in our understanding of the early universe have revealed that faster-than-light expansion occurred during the first fraction of a second after the Big Bang. This period, called cosmic inflation, involved the exponential expansion of space at rates far exceeding the speed of light. During inflation, regions of space that were initially in close contact were carried apart faster than light could travel between them, creating the large-scale structure we observe in the universe today. The fields that drove cosmic inflation might still exist in the universe, creating pockets of faster-than-light expansion in remote regions of space. Some theories propose that new universes are constantly being created through this inflationary process, with each new universe expanding faster than light away from its parent universe. If this is true, then faster-than-light expansion might be occurring all around us at scales too vast for us to observe directly. The search for evidence of faster-than-light phenomena in our immediate cosmic neighborhood has led to investigations of anomalous astronomical observations. Some gamma-ray bursts, the most energetic explosions in the universe, appear to emit jets of material moving faster than light when observed from Earth. While these observations can usually be explained by relativistic effects that create the illusion of faster-than-light motion, some cases remain puzzling and might involve genuine superluminal processes. Pulsars, rapidly rotating neutron stars that emit beams of radiation like cosmic lighthouses, sometimes exhibit timing anomalies that are difficult to explain using conventional physics. Some researchers have proposed that these anomalies might be evidence of faster-than-light processes occurring in the extreme gravitational and magnetic environments around neutron stars. The intense fields in these environments might create conditions where normal space and time break down, allowing faster-than-light phenomena to emerge. The study of consciousness and its relationship to physical reality has led some researchers to propose that mental processes might involve faster-than-light information transfer. The binding problem in neuroscience, which concerns how the brain integrates information from different sensory modalities into unified conscious experiences, might require faster-than-light coordination between different brain regions. While these ideas remain highly speculative, they suggest that consciousness itself might transcend the normal limitations of space-time. Some theories propose that consciousness is not produced by the brain, but is instead a fundamental feature of the universe that the brain taps into through quantum processes. If consciousness operates through faster-than-light quantum channels, then every conscious being might already be connected to a universal field of awareness that transcends space and time. This could explain phenomena like intuition, telepathy, and other experiences that seem to involve faster-than-light information transfer. The possibility that we are already surrounded by faster-than-light phenomena suggests that our understanding of the cosmic speed limit is incomplete. The speed of light might be a barrier only for certain types of information and energy transfer, while other forms of influence and correlation routinely exceed this limit. The universe might be far more interconnected and dynamic than our current theories suggest, with faster-than-light processes playing crucial roles in everything from quantum mechanics to consciousness. As we continue to explore the deepest mysteries of physics and cosmology, we may discover that faster-than-light phenomena are not exotic exceptions to the rules of nature, but fundamental features of reality that we have simply failed to recognize. The cosmic speed limit might be less like a universal law and more like a local restriction that applies only to certain types of matter and energy under specific circumstances. If this is true, then the question is not whether we can learn to travel faster than light, but whether we can learn to recognize and harness the faster-than-light processes that already surround us. The key to transcending the speed of light might not require building exotic technologies or discovering new physics, but simply developing a deeper understanding of the hidden, faster-than-light phenomena that permeate every aspect of our existence. As we contemplate the vast cosmos surrounding our small blue planet, a profound question emerges from the silence between the stars. If faster-than-light travel is possible, where are all the aliens? This question, known as the Fermi paradox after physicist Enrico Fermi, who first posed it in 1950, suggests that if the universe is teeming with intelligent life, and if faster-than-light travel is achievable, then evidence of alien civilizations should be everywhere. The absence of such obvious evidence has led scientists to search for more subtle signs that advanced extraterrestrial beings might already be using technologies that transcend the cosmic speed limit. The search for extraterrestrial intelligence, known as SETI, has been scanning the heavens for over 6 decades, listening for radio signals that might indicate the presence of alien civilizations. Traditional SETI searches look for narrow-band radio transmissions or other electromagnetic signals that could not occur naturally and therefore must be of artificial origin. However, some researchers have proposed that truly advanced civilizations might use faster-than-light communication methods that would be invisible to our current detection techniques. If aliens possess faster-than-light communication technology, they might have abandoned radio waves entirely in favor of quantum entanglement networks, tachyonic transmissions, or other exotic communication methods that we cannot currently detect. This could explain why decades of radio searches have failed to find definitive evidence of extraterrestrial intelligence. We might be looking for signals in the wrong part of the electromagnetic spectrum, or we might need to develop entirely new detection methods to observe faster-than-light communications. Some SETI researchers have proposed searching for the signatures of faster-than-light technologies themselves, rather than the communications they enable. A civilization using warp drives would need to manipulate enormous amounts of exotic matter and energy, processes that might leave detectable traces in the fabric of space-time. These signatures could include gravitational wave emissions, unusual patterns of electromagnetic radiation, or distortions in the background radiation that permeates the universe. The construction and operation of wormhole networks would also likely produce observable effects. The exotic matter required to stabilize wormholes might emit characteristic radiation signatures or create unique gravitational field patterns. The mouths of artificial wormholes might appear as unusual astronomical objects that cannot be explained by conventional astrophysics. Some researchers have proposed that certain mysterious astronomical phenomena, such as fast radio bursts or gamma-ray bursts, might actually be signatures of alien wormhole technology. The concept of Dyson spheres, megastructures that advanced civilizations might build around their stars to capture energy, has been extended to include technologies that could enable faster-than-light travel. A civilization capable of building Dyson spheres would have access to the enormous energy resources needed to power warp drives or create stable wormholes. The construction of such megastructures might therefore be a precursor to the development of faster-than-light technologies. Recent astronomical discoveries have identified several objects that exhibit unusual properties that could potentially be explained by advanced alien technology. The star, KIC 8462852, nicknamed Tabby's star, after astronomer Tabetha Boyajian, who first studied it, displays irregular dimming patterns that are difficult to explain using known natural phenomena. While most scientists believe the dimming is caused by dust clouds or other natural processes, some researchers have speculated that it could be evidence of massive alien engineering projects. The interstellar object Oumuamua, which passed through our solar system in 2017, exhibited several unusual characteristics that sparked speculation about its artificial origin. The object had an extremely elongated shape unlike any known asteroid or comet, and it appeared to accelerate away from the Sun in a manner that could not be explained by gravitational forces alone. While most astronomers believe Oumuamua is a natural object with unusual properties, some researchers have proposed that it could be an alien probe using exotic propulsion technology. The phenomenon of unidentified aerial phenomena, formerly known as UFOs, has gained renewed scientific attention in recent years, following the release of military videos showing objects that appear to exhibit flight characteristics beyond the capabilities of known human technology. Some of these objects appear to accelerate instantaneously, change direction without regard for inertia, and move at speeds that would be impossible for conventional aircraft. While most scientists remain skeptical that these observations represent alien technology, they have sparked new interest in the possibility that we might already be witnessing evidence of faster-than-light propulsion systems. The study of these unidentified phenomena has revealed flight patterns and capabilities that seem to violate our understanding of physics. Objects have been observed to accelerate from a standstill to hypersonic speeds in fractions of a second, with no visible propulsion system and no sonic booms or other signatures that would be expected from conventional propulsion. Some objects appear to transition seamlessly between air and water, maintaining their flight characteristics in both media, without any apparent modification of their propulsion systems. If these observations represent genuine advanced technology rather than measurement errors or natural phenomena, they might indicate the presence of propulsion systems that manipulate space-time itself, rather than relying on conventional reaction-based propulsion. Such systems could potentially enable faster-than-light travel by creating localized distortions in the fabric of space and time around the vehicle. The search for evidence of alien faster-than-light technology has also focused on astronomical phenomena that might indicate large-scale engineering projects. Some researchers have proposed that advanced civilizations might use faster-than-light travel to spread throughout the galaxy, creating networks of colonies and infrastructure that would be detectable from Earth. The absence of obvious signs of such galactic colonization has led to speculation that faster-than-light travel might be more difficult than we imagine, or that alien civilizations might be deliberately hiding their presence from younger species like ourselves. The concept of a galactic internet, a faster-than-light communication network spanning the entire Milky Way galaxy, has captured the imagination of scientists and science fiction writers alike. Such a network would enable instantaneous communication between civilizations separated by thousands of light years, allowing for the coordination of activities and the sharing of information on a galactic scale. The energy requirements for such a network would be enormous, but an advanced civilization with access to the resources of multiple star systems might be able to construct and maintain it. Some researchers have proposed that we might already be embedded within such a galactic communication network without realizing it. If alien civilizations use quantum entanglement or other exotic communication methods, their transmissions might be passing through our solar system constantly, without our detection equipment being able to recognize them. We might be like primitive humans trying to detect radio waves with Stone Age technology, completely unaware of the sophisticated communications happening all around us. The search for technosignatures, artificial modifications to astronomical objects that could only be created by intelligent beings, has become an increasingly important component of SETI research. These signatures might include artificial structures around stars, unusual isotope ratios in stellar atmospheres that could indicate nuclear engineering, or patterns of stellar dimming that suggest the presence of massive solar collectors or other megastructures. Some technosignatures might be specifically related to faster-than-light technologies. The exotic matter required for warp drives and wormholes might need to be manufactured using processes that leave distinctive signatures in the electromagnetic spectrum. The testing of faster-than-light propulsion systems might produce characteristic radiation patterns or gravitational wave emissions that could be detected by sensitive instruments on Earth. The possibility that alien civilizations might be using faster-than-light travel to visit Earth has been a subject of speculation and controversy for decades. If such visits are occurring, they might explain some of the unidentified aerial phenomena that have been reported by military personnel and civilian witnesses. However, the vast majority of such reports can be explained by conventional phenomena, and no definitive evidence of alien visitation has been established. The challenge of detecting alien faster-than-light technology is compounded by our limited understanding of what such technology might look like. We are searching for evidence of technologies that we ourselves do not possess, and may not even understand. It is possible that alien faster-than-light systems operate on principles that are completely foreign to our current scientific paradigms, making them effectively invisible to our detection methods. Some researchers have proposed that we should expand our search strategies to include phenomena that seem impossible according to our current understanding of physics. Instead of dismissing anomalous observations as measurement errors or natural phenomena, we should carefully investigate them to determine whether they might represent evidence of technologies that transcend our current scientific knowledge. The question of whether we have already detected evidence of alien faster-than-light technology, but failed to recognize it, remains open. Our scientific instruments record vast amounts of data from across the electromagnetic spectrum, and it is possible that signatures of exotic propulsion or communication systems are hidden within this data, waiting to be discovered by researchers who know what to look for. The development of artificial intelligence and machine learning techniques has opened new possibilities for analyzing astronomical data in search of technosignatures. These systems can identify subtle patterns and anomalies that might be missed by human researchers, potentially revealing evidence of alien technology that has been hiding in plain sight within our existing datasets. As our detection capabilities continue to improve and our understanding of exotic physics deepens, we may eventually be able to definitively answer the question of whether alien civilizations are already using faster-than-light technologies. The discovery of such evidence would revolutionize our understanding of physics and our place in the universe, confirming that the cosmic speed limit can indeed be transcended and that we are not alone in our quest to explore the stars. Whether we find evidence of alien faster-than-light technology or continue to encounter only silence from the cosmos, the search itself pushes us to expand our understanding of what is possible and to develop new technologies that might one day enable us to join the hypothetical community of faster-than-light traveling civilizations that may already exist among the stars. In our searching, we grow closer to answering one of the most profound questions that has ever captured human imagination. Are we alone? And if not, how do our cosmic neighbors traverse the vast distances between the worlds? As we stand at the threshold of a new era in space exploration, with private companies launching astronauts to orbit and nations planning missions to Mars, a deeper question emerges about the ultimate future of human space travel. Will we forever remain confined to our local cosmic neighborhood by the speed of light? Or will we eventually develop technologies that allow us to transcend this fundamental barrier and venture forth to explore distant worlds among the stars? The current state of space propulsion technology represents both remarkable achievements and sobering limitations. Our most advanced spacecraft, powered by chemical rockets that burn fuel and expel reaction mass, can reach speeds of only a few tens of kilometers per second. At these velocities, a journey to our nearest stellar neighbor, Proxima Centauri, would take over 70,000 years. Even the fastest human-made object, the Parker Solar Probe, which will reach speeds of over 200 kilometers per second as it approaches the Sun, would still require 20,000 years to reach the nearest star. This vast gulf between our current capabilities and the speeds required for interstellar travel has led engineers and physicists to explore revolutionary new propulsion concepts that could dramatically increase spacecraft velocities. Ion drives, which use electric fields to accelerate charged particles to very high speeds, can achieve much greater fuel efficiency than chemical rockets, though they produce very low thrust and require long periods of acceleration to reach high velocities. More exotic propulsion concepts include fusion rockets, which would harness the energy released by nuclear fusion reactions to propel spacecraft at significant fractions of the speed of light. Fusion fuel is abundant throughout the universe in the form of hydrogen, and fusion reactions release enormous amounts of energy per unit mass of fuel. A fusion-powered spacecraft might eventually reach speeds of 10 to 20% of light speed, reducing interstellar journey times to decades rather than millennia. Antimatter propulsion represents the ultimate in conventional rocket technology. When matter and antimatter particles collide, they annihilate completely, converting their entire mass into energy according to Einstein's famous equation. This makes antimatter the most energy-dense fuel possible, capable of propelling spacecraft to speeds approaching the speed of light. However, antimatter is extraordinarily difficult and expensive to produce, and storing it safely poses enormous technical challenges. Even if we could overcome the practical difficulties of antimatter propulsion, relativistic effects would become increasingly important as spacecraft approach the speed of light. Time dilation would cause years or decades to pass on Earth during journeys that seem much shorter to the travelers. The energy requirements for acceleration would increase dramatically as velocities approach light speed, making it impossible to reach or exceed the cosmic speed limit using conventional propulsion. These limitations have motivated researchers to investigate propulsion concepts that transcend conventional rocket technology entirely. The theoretical foundations for faster-than-light travel that we have explored in previous chapters suggest several possible pathways that future civilizations might pursue in their quest to explore the galaxy. The development of warp drive technology represents perhaps the most promising approach to achieving faster-than-light travel. While current estimates suggest that the energy requirements for Alcubierre drives are far beyond our present capabilities, ongoing theoretical research continues to find ways to reduce these requirements. Some recent proposals suggest that the exotic matter needed for warp drives might be created using carefully designed quantum field configurations that amplify naturally occurring vacuum fluctuations. Laboratory experiments in quantum optics and condensed matter physics have already demonstrated the ability to create regions of negative refractive index, where light appears to travel backward through specially designed materials called metamaterials. These experiments hint at the possibility that we might eventually learn to create larger regions of exotic matter with the properties needed for warp drive propulsion. The field of quantum engineering is advancing rapidly, with researchers developing increasingly sophisticated techniques for manipulating quantum systems at the microscopic level. As these techniques mature and scale up to macroscopic systems, we might eventually gain the ability to engineer the vacuum of space itself, creating the exotic space-time geometries required for faster-than-light travel. Breakthroughs in our understanding of dark matter and dark energy could also open new pathways to faster-than-light propulsion. These mysterious components of the universe, which together make up over 95% of all matter and energy, remain largely unknown to science. Dark energy appears to be responsible for the accelerating expansion of space itself, suggesting that it might be possible to harness this expansion for propulsion purposes. If dark matter particles can indeed travel faster than light under certain circumstances, as some theoretical models suggest, then learning to create and control dark matter could provide access to faster-than-light propulsion systems. The development of dark matter manipulation technology would represent a revolution in physics comparable to the harnessing of electromagnetic forces or nuclear energy. The construction of artificial wormholes represents another potential pathway to faster-than-light travel. While the energy requirements for creating traversable wormholes are currently beyond our capabilities, advances in our understanding of quantum gravity and the fundamental structure of space-time might reveal new approaches to wormhole engineering. Some theoretical models suggest that microscopic wormholes might constantly appear and disappear in the quantum foam of space-time at the smallest scales. If these natural quantum wormholes could be captured, enlarged, and stabilized, they might provide the foundation for macroscopic wormhole transportation networks. The technology required for such manipulation would need to operate at energy scales comparable to those present during the first moments after the Big Bang, but it would not necessarily require the creation of exotic matter from scratch. The development of room temperature, superconductors, and other advanced materials could play a crucial role in enabling faster-than-light technologies. Superconductors can carry electrical currents without resistance, allowing for the creation of extremely powerful magnetic fields that might be used to manipulate space-time or control exotic matter. Advances in nanotechnology and materials science continue to reveal new materials with properties that seemed impossible just decades ago. Artificial intelligence and quantum computing may also prove essential for developing faster-than-light propulsion systems. The mathematical calculations required to design and control warp drives or wormholes are enormously complex, involving non-linear differential equations that describe the behavior of curved spacetime. Quantum computers, which can perform certain types of calculations exponentially faster than classical computers, might eventually become powerful enough to solve these equations in real time. Machine learning algorithms could help us discover new solutions to Einstein's field equations that permit faster-than-light travel with lower energy requirements. These algorithms can explore vast mathematical spaces much more efficiently than human researchers, potentially finding exotic spacetime geometries that we have never considered. The combination of artificial intelligence and advanced physics simulations might reveal entirely new approaches to transcending the speed of light. The timeline for developing faster-than-light technology remains highly uncertain. Conservative estimates suggest that such capabilities might emerge within the next few centuries, assuming continued exponential growth in our scientific understanding and technological capabilities. More optimistic projections propose that breakthrough discoveries in fundamental physics could accelerate this timeline dramatically, potentially making faster-than-light travel possible within the next century. However, it is also possible that faster-than-light travel will prove to be fundamentally impossible, regardless of how advanced our technology becomes. The laws of physics might contain absolute prohibitions against exceeding the speed of light that cannot be circumvented through any amount of cleverness or technological sophistication. The cosmic speed limit might truly be absolute, confining all intelligent life to relatively small regions of the universe. Even if faster-than-light travel proves impossible, significant advances in conventional propulsion technology could still enable practical interstellar exploration. Fusion-powered spacecraft capable of reaching 10 to 20% of light speed would make journeys to nearby star systems feasible within human lifetimes. Robotic probes traveling at such speeds could explore hundreds of star systems within a few centuries, potentially discovering evidence of extraterrestrial life or suitable worlds for human colonization. The development of advanced life support systems and closed-loop ecological technologies could enable generation ships that sustain human populations during multi-century journeys to distant stars. While such voyages would require enormous commitments of resources and human dedication, they would make possible the gradual spread of human civilization throughout the galaxy over timescales of millions of years. Advances in medical technology, including life extension therapies and suspended animation systems, could make even very long interstellar journeys practical for human travelers. If human lifespans could be extended indefinitely, or if travelers could be placed in suspended animation for the duration of their journeys, then even conventional spacecraft traveling at modest fractions of light speed could enable exploration of the entire galaxy. The social and political challenges of developing faster-than-light technology may prove as formidable as the technical challenges. Such technology would require unprecedented levels of international cooperation and resource allocation. The energy requirements alone would likely exceed the total energy production of our entire civilization by many orders of magnitude, demanding the development of fusion power, space-based solar collectors, or other advanced energy technologies. The potential military applications of faster-than-light technology would also create new security concerns and arms race dynamics. Nations or organizations that first achieve faster-than-light capabilities would gain enormous strategic advantages, potentially destabilizing international relations and creating new forms of conflict. The governance and regulation of faster-than-light technology would require new international frameworks and institutions. Despite these challenges, the potential benefits of achieving faster-than-light travel are so enormous that the effort to develop such capabilities seems inevitable. Faster-than-light technology would transform humanity from a single-planet species to a truly galactic civilization, providing access to unlimited resources and opportunities for expansion and development. It would enable us to explore and understand the universe on scales that are currently unimaginable, potentially revealing new forms of life and intelligence that could expand our understanding of existence itself. The quest to surpass the speed of light represents the ultimate expression of human curiosity and ambition. Whether we succeed in this endeavor or discover that the cosmic speed limit truly is absolute, the journey itself will advance our understanding of physics and technology in ways that benefit all aspects of human civilization. In reaching for the stars, we inevitably reach new heights of knowledge and capability that transform our world and our understanding of our place in the cosmos. As we near the end of our journey through the mysteries of faster-than-light travel, we must pause to contemplate the profound philosophical and existential implications that such capabilities would have for humanity and our understanding of existence itself. The ability to transcend the cosmic speed limit would not merely represent a technological achievement, but a fundamental transformation in what it means to be human and our relationship with the universe around us. For as long as humans have gazed up at the night sky, we have been defined by our cosmic isolation. The vast distances between stars, measured in years and decades and centuries of light travel time, have created an existential loneliness that permeates our deepest thoughts about our place in the universe. We are, in Carl Sagan's famous words, alone on our pale blue dot, separated from any potential cosmic neighbors by gulfs of space so vast that they seem to render communication or contact impossible. This isolation has shaped not only our science and technology, but our philosophy, religion, and literature. The human condition has been fundamentally characterized by our confinement to a single world, our knowledge that we are part of a vast cosmos, but our inability to reach beyond our immediate cosmic neighborhood. We have been cosmic prisoners, able to observe the universe but unable to truly explore it or connect with whatever other forms of life and intelligence it might contain. The development of faster-than-light travel would shatter this cosmic prison and transform humanity from a planetary species into a truly galactic civilization. But such a transformation would bring with it philosophical challenges and existential questions that we have never before had to confront. What would it mean to be human when we are no longer confined to Earth? How would our sense of identity and purpose evolve when we have access to unlimited worlds and unlimited possibilities? The concept of home itself would be fundamentally altered by faster-than-light travel. Throughout human history, our identity has been rooted in specific places: the village where we were born, the nation where we hold citizenship, the planet that gave birth to our species. But when humans can travel instantly between worlds separated by hundreds or thousands of light years, what meaning would geographical identity retain? Would we still think of ourselves as Earthlings, or would we develop new forms of identity based on galactic regions or star systems? The experience of time would also be transformed by faster-than-light capabilities. Currently, our lives are measured against the backdrop of cosmic timescales that dwarf human existence. The light from distant stars that we see tonight began its journey before humans existed, creating a sense of our own temporal insignificance. But faster-than-light travel would allow us to move through space faster than information can propagate, potentially enabling us to reach distant locations before light from our departure has had time to arrive. This could create strange temporal paradoxes where we witness our own past actions or receive information about events that have not yet occurred from our perspective. The philosophical implications of causality violations that might arise from faster-than-light travel present some of the most challenging questions in all of physics and philosophy. If we could send information faster than light, we might be able to influence our own past, creating causal loops where effects precede their causes. This would challenge our most basic assumptions about free will, determinism, and the nature of reality itself. Consider the paradox of meeting your own past self through faster-than-light travel. If you could travel to a distant location faster than light, then return to Earth before the light from your departure had arrived, you might encounter yourself as you existed before you left. Which version of yourself would be the real you? How would such encounters affect your sense of personal identity and continuity? The discovery that faster-than-light travel is possible would also have profound implications for our understanding of physics and the nature of reality. It would suggest that our current theories, including Einstein's relativity, are incomplete approximations to a deeper truth about the universe. This could trigger a scientific revolution comparable to the transition from Newtonian physics to quantum mechanics and relativity, fundamentally altering our understanding of space, time, matter, and energy. Such a revolution would likely reveal that the universe is far stranger and more wonderful than we currently imagine. New forms of matter and energy, new dimensions of space and time, new principles of causality and logic might all emerge from the physics that enables faster-than-light travel. Our entire conceptual framework for understanding reality might need to be rebuilt from the ground up. The religious and spiritual implications of faster-than-light travel would be equally profound. Many religious traditions have been shaped by the assumption that Earth is humanity's permanent home, the stage upon which our spiritual development unfolds. The ability to travel instantly to other worlds would challenge these traditions to expand their understanding of divine purpose and human destiny. Some religious thinkers might interpret faster-than-light travel as evidence of divine favor, a gift that enables humanity to fulfill its cosmic purpose by spreading consciousness and spirituality throughout the universe. Others might see it as a test of human wisdom and moral development, a capability that could lead either to enlightenment or to cosmic catastrophe, depending on how it is used. The encounter with alien civilizations that faster-than-light travel would make possible could also transform human religious and philosophical thought. The discovery that intelligence and consciousness exist elsewhere in the universe would challenge anthropocentric worldviews and force us to reconsider our assumptions about the uniqueness and significance of human existence. Different alien species might have developed entirely different approaches to philosophy, ethics, and spirituality based on their unique evolutionary histories and environmental conditions. Exposure to these alternative ways of thinking could expand human consciousness in ways that are difficult to imagine, potentially revealing new dimensions of existence that we have never considered. The ethical implications of faster-than-light travel would present unprecedented moral challenges. With the ability to reach any point in the galaxy almost instantly, humanity would gain enormous power over the cosmic environment. How would we use this power responsibly? What obligations would we have to protect alien ecosystems and civilizations? How would we prevent faster-than-light technology from being used for destructive purposes? The development of faster-than-light weapons could make possible forms of warfare that transcend anything in human experience. Battles could be fought across galactic distances with weapons that arrive before their approach can be detected. Entire star systems could be destroyed by attacks launched from thousands of light years away. The governance and control of such weapons would require new forms of international cooperation and regulation that do not currently exist. The social and economic structures of human civilization would also be transformed by faster-than-light travel. When goods, people, and information can move instantly across galactic distances, traditional concepts of scarcity, distance, and time would lose much of their meaning. New forms of economic organization would emerge to manage the flow of resources across a galactic civilization, spanning hundreds of billions of star systems. The concept of privacy and personal space would be challenged when faster-than-light travel makes it possible to reach any location in the galaxy almost instantly. How would individuals maintain their autonomy in solitude when distance no longer provides protection from unwanted contact? New social norms and legal frameworks would need to evolve to protect individual rights in a universe where physical barriers have been eliminated. The psychological impact of faster-than-light travel on individual human beings would be profound and unpredictable. Our minds evolved to cope with the limited spatial and temporal scales of life on a single planet. How would human psychology adapt to the vastness of galactic civilization? Would the unlimited possibilities created by faster-than-light travel lead to greater fulfillment and happiness? Or would they create new forms of anxiety and existential crisis? Some individuals might experience a form of cosmic agoraphobia, becoming overwhelmed by the infinite possibilities that faster-than-light travel creates. Others might develop addiction, like dependencies on constant travel and stimulation, never able to find satisfaction in any single location or experience. The mental health implications of faster-than-light travel would require entirely new approaches to psychology and therapy. The preservation of human culture and diversity would become both more important and more challenging in a galactic civilization. With faster-than-light travel enabling instant communication and transportation across vast distances, there would be strong pressures toward cultural homogenization. How would humanity maintain its rich diversity of languages, traditions, and ways of life when all cultures are in constant contact with each other? Conversely, faster-than-light travel might enable the development of entirely new forms of human culture, adapted to specific galactic environments. Humans living near the galactic core might develop different customs and perspectives than those living in the outer spiral arms. New forms of art, music, and literature might emerge that reflect the unique experiences of galactic civilization. The question of human enhancement and evolution would take on new urgency in a galactic context. Would natural human biology be adequate for life in the diverse environments found throughout the galaxy? Would we need to enhance ourselves genetically, cybernetically, or through other means to thrive in our expanded cosmic home? Such enhancements might gradually transform humanity into something entirely new, raising questions about what it means to remain human. The ultimate philosophical question raised by faster-than-light travel concerns the purpose and meaning of existence itself. If the universe is truly infinite and we have the ability to explore it without limit, what goals should guide our cosmic expansion? What would constitute a meaningful life when all possibilities are available? How would we find purpose and direction in a universe where distance and time no longer constrain our choices? Some philosophers might argue that faster-than-light travel would represent the ultimate liberation of human consciousness, freeing us from all physical limitations to pursue pure knowledge and understanding. Others might contend that limitations and constraints are essential for meaning and purpose, and that unlimited possibilities would lead to nihilism and despair. The development of faster-than-light travel would mark a transition point in human evolution, comparable to the development of language, agriculture, or technology. It would transform us from a terrestrial species into something fundamentally new, a cosmic civilization capable of exploring and inhabiting the entire universe. Whether this transformation would ultimately enhance or diminish human existence remains one of the greatest questions we face as we contemplate our potential cosmic future. As we drift toward the conclusion of our exploration, we are left with the profound realization that faster-than-light travel represents more than just a technological goal. It embodies humanity's deepest aspirations to transcend limitations, explore the unknown, and discover our true place in the cosmic order. Whether we achieve this capability or discover that it remains forever beyond our reach, the quest itself transforms us and expands our understanding of what it means to exist in this vast and mysterious universe. As we reach the end of our journey through the mysteries of faster-than-light travel, we find ourselves in a place of profound contemplation. We have explored the theoretical foundations of warp drives and wormholes, delved into the quantum realm of entanglement and possibility, examined the evidence for phenomena that already transcend the cosmic speed limit, and contemplated the transformative implications that such capabilities would have for human civilization and consciousness. Throughout this exploration, one theme has emerged again and again. The boundaries that seem absolute and insurmountable often prove to be illusions created by the limitations of our current understanding. Time and again in the history of science, phenomena that were once thought to be impossible have become not only possible, but commonplace. Flight was impossible until the Wright brothers took to the skies. Heavier-than-air machines could never fly until they did. The atom was indivisible until we split it. Space travel was fantasy until we walked on the moon. The speed of light has stood for over a century as the ultimate barrier, the final frontier that cannot be crossed. Einstein's equations seem to close the door forever on faster-than-light travel, establishing the cosmic speed limit as an absolute law of nature. Yet, as we have seen throughout our journey, those same equations also provide pathways around their own limitations. They permit the existence of warp bubbles that carry objects faster than light without violating relativity. They allow for wormholes that connect distant regions of space-time through shortcuts that bypass the normal constraints of distance and time. The universe reveals itself to be far more flexible and creative than our initial theories suggested. Space and time, which once seemed like fixed and unchanging backdrops for physical events, prove to be dynamic and malleable. They can be stretched and compressed, folded and tunneled, manipulated and engineered by sufficiently advanced technology. The cosmic speed limit that seems so absolute may be more like a local traffic law than a fundamental principle of reality. Even in the quantum realm, we find evidence that nature routinely transcends the boundaries we try to impose upon it. Particles tunnel through barriers instantaneously, regardless of their thickness. Entangled particles share correlations that propagate faster than light across any distance. The vacuum of space itself seethes with virtual particles and quantum fluctuations that hint at hidden layers of reality beyond our everyday experience. Perhaps most intriguingly, the universe itself demonstrates faster-than-light behavior through its own expansion. Space grows and stretches, carrying distant galaxies away from us at speeds that dwarf the velocity of light. This cosmic expansion shows us that faster-than-light motion is not forbidden by the laws of physics, but is actually built into the fundamental structure of reality itself. As we have explored the search for evidence of alien civilizations and their potential technologies, we have discovered that the absence of obvious signs of extraterrestrial intelligence might itself be evidence of capabilities that transcend our current understanding. Advanced civilizations might have moved beyond the electromagnetic spectrum that we monitor, communicating and traveling through channels that are invisible to our present detection methods. The mysterious phenomena we observe in our skies, from unidentified aerial objects to anomalous astronomical events, remind us that the universe still holds secrets that we have not yet learned to interpret. What seems impossible according to our current theories might simply represent technologies or natural processes that operate according to principles we have not yet discovered. Looking toward the future of human space exploration, we see a species standing at the threshold of cosmic expansion. Our current chemical rockets represent only the first tentative steps toward the stars. Like the earliest stone tools in the development of human technology, the fusion rockets, antimatter engines, and exotic propulsion systems of tomorrow will carry us faster and farther, but they too may prove to be only waypoints on the journey toward truly transformative capabilities. The development of faster-than-light travel, whether through warp drives, wormholes, or technologies we have not yet imagined, would represent more than just an advance in transportation. It would mark humanity's graduation from a planetary to a galactic species, opening up possibilities for exploration, discovery, and growth that are currently beyond our ability to envision. Yet even if faster-than-light travel ultimately proves to be impossible, the pursuit of this capability drives us to push the boundaries of science and technology in ways that benefit all aspects of human civilization. The quest to transcend the speed of light leads us to deeper understanding of space and time, matter and energy, quantum mechanics and relativity. These insights find applications in computing and communication, energy and medicine, expanding our capabilities, even if they do not ultimately enable us to reach the stars. The philosophical and existential implications of our exploration remind us that the question of faster-than-light travel touches the deepest aspects of human nature. We are a species defined by our curiosity, our refusal to accept limitations, our determination to explore and understand the universe around us. Whether the cosmic speed limit can be transcended or not, the very act of questioning it, investigating it, and pushing against it represents the essence of what makes us human. In the end, perhaps the most important lesson from our journey is that the universe is far stranger, more wonderful, and more full of possibilities than we ever dared to imagine. Every generation of scientists has believed that they were approaching a complete understanding of nature, only to discover new layers of mystery and complexity that revealed how much they still did not know. We stand today in much the same position, confident in some aspects of our knowledge, but aware that vast territories of understanding remain to be explored. The speed of light may represent an absolute barrier, or it may be just another boundary waiting to be transcended by deeper insight and more advanced technology. We do not yet know which possibility will prove correct, but the exploration itself expands our horizons and enriches our understanding of existence. As you drift off to sleep tonight, carry with you the wonder and possibility that our exploration has revealed. Let your mind wander through the cosmos at speeds faster than light, visiting distant worlds and encountering the marvels that await discovery among the stars. In your dreams, you are already a citizen of the galaxy, unbound by the limitations that seem to constrain us today. The universe is vast beyond measure, filled with mysteries that beckon to be solved and wonders that await our discovery. The speed of light has been our companion and our guide for over a century, teaching us about the fundamental nature of space and time. But like all the boundaries that human curiosity has encountered throughout history, it may ultimately prove to be not a wall that confines us, but a door that opens onto realms of possibility we have not yet learned to imagine. The story of faster-than-light travel is still being written, in laboratories and observatories around the world, in the theoretical calculations of physicists and the dreams of explorers, in the endless human quest to push beyond every limit and explore every frontier. Whether that story ends with triumph or teaches us that some boundaries are indeed absolute, it will continue to inspire us to reach for the impossible and to never stop wondering what lies beyond the next horizon. Tonight, as you close your eyes and let consciousness drift away, remember that you are part of a species that has never encountered a frontier it did not eventually cross, never faced a mystery it did not ultimately solve, never met a limit it did not strive to transcend. The speed of light may be the ultimate challenge, but you are part of the universe's own attempt to understand itself. And in that quest, no dream is too bold, no question too ambitious, no goal too distant to pursue. The cosmos awaits, vast and mysterious and full of promise. Sweet dreams, fellow traveler, as we journey together through the infinite night toward whatever wonders tomorrow may bring.